Hey guys, in this video we're going to go through proofs by contradiction which involve inequalities. So we're going to solve these three exercises right here. The first two, they involve algebraic manipulation, and the third one involves trig, which means that we might need to use trig identities in order to disprove our assumption not P. And we're also going to go through how to negate an inequality, and we're going to arrive when developing that negation to a contradiction, to some sort of nonsense, such as, for example, 1 is greater than 2, for example. This is just an example. And also let's use this opportunity to go to through the five-step process in solving proofs by contradiction. Let's actually start with that. So how do we prove by contradiction? Number one, we need to state the proposition which is given by the exercise. And in proofs by contradiction, it might be something like prove by contradiction that there are infinitely many prime numbers, or prove by contradiction that log 3 base 2 is an irrational number. In our case, in exercise 1, for example, what we have is prove by contradiction that 1 over 2 root n plus 1 is less than root of n plus 1 minus root of n. So that's our proposition. Number two, we're going to assume that the negation of P is true. So we're going to assume that the complete opposite of P is true, which means in exercise number 1, and we're going to go through it with a little bit more detail later on. In that case, we'll assume that 1 over 2 root n plus 1 is not less than, but greater than or equal to the root of n plus 1 minus the root of n. And it's important to state right now that the negation of less than is not greater than, it's actually greater than or equal to, and the negation of greater than is less than or equal to. Now we have two other possibilities, less than or equal to, which becomes greater than, or greater than or equal to, which becomes less than. So these are the four possibilities when you have inequalities. Now back to the five-step recipe. Number three, we're going to develop the proof. And what does that mean? It means that you're going to use the assumption not P along with an algebraic process or axioms or facts in order to disprove your not P, which means that P will be right. What does it mean in this case? You started with the less than sign. You assumed the negation, which is greater than or equal to. Then you're going to develop an algebraic process. You're going to, by only using valid manipulations, simplify, factor, work it out in order to get somewhere. You will eventually get somewhere that does not make sense, or something that does not make sense. You will get some nonsense, such as, for example, and this is just a silly example, 1 is greater than 2. That's not exactly what's going to happen here, but it will also be a false statement, which allows us to arrive at a contradiction. Do notice the difference between these two. Getting a contradiction because you made some manipulation which is simply wrong, versus manipulating the expression correctly and getting to a false statement. Only the second one is a valid method. Number four, once you get to the contradiction, you're going to identify that that's where the contradiction lies and why that is the case. Let's say, just as an example, that you're trying to prove that a number is odd, and then you arrive at this. N is equal to 2 times 3k plus 1, something like this. And we know that every multiple of 2 is even. Therefore, you would write something like this. Given that n is a multiple of 2, n is even, which contradicts the initial assumption that n is an odd number. It will look something like this. For inequalities, it will be a little bit different. We're going to see through the three examples that we're going to solve in this video. And then number 5, which is quite fast, it is to write the conclusion. Writing the conclusion is simply stating, therefore, by contradiction, P, which is the proposition that we stated before, is true. Now let's apply all of these 5 steps in the 3 exercises that we have in front of us. Now let's tackle exercise number 1, which is this proof by contradiction. We have something which is less than something else for all positive real numbers. The negation of P will be greater than or equal to, as we saw before. Now on the first step, we're going to let P, the proposition P, be 1 over 2 root n plus 1 less than, and this is what we're trying to prove, root of n plus 1 minus the root of n. We're not going to change anything in this step. We're going to change it in the second one. Assume not p, and this is the symbol for not p. You can write not p like this as well, or just simply not p. So any of these three is fine. And you also, of course, have to state what is not p. In this case, 1 over 2 root of n plus 1 is greater than or equal to the root of n plus 1 minus the root of n. Now we'll carry this out and we're going to get some sort of nonsense towards the end. Let's see what we can do here. We're talking about a positive real number n, which means that the root of n plus 1 will also be positive, and if you multiply it by 2, it will be positive as well. Therefore, we can cross multiply 2 root of n plus 1 without changing the direction of the inequality. So we have 1 is greater than or equal to 2 root n plus 1 times the right hand side, which is the root of n plus 1, minus the root of n. We can FOIL the 2 root of n plus 1, getting in the next step 2 times n plus 1 without a root, given that the product between these two is equal to n plus 1, minus 2 root of n plus 1 times the root of n. Now this is simply 2n plus 2, and we can remove or subtract 1 from both sides, which gives us 0 is greater than or equal to 2n plus 1 minus 2 root of n plus 1 times the root of n. Now we can not only rewrite this as the root of n times n plus 1, but also move it to the left hand side or add that to both sides, which is the same thing. So we get 2 root of n times n plus 1 greater than or equal to 2n plus 1. Now, given that we're talking about positive real numbers, we can square both of these sides, the left hand side and the right hand side, without having to worry about the direction of this inequality. So that's what we're going to do right now. And we do that so we can completely remove the root. On the left hand side, we get 4 times n plus 1 greater than or equal to 2n plus 1 squared, which is 4n squared plus 4n plus 1. So we get 4n squared plus 4n greater than or equal to 4n squared plus 4n plus 1. And right now, we can already see the contradiction, because if you simplify these terms, we get 0 greater than or equal to 1, which of course is a contradiction. And then we write the conclusion. Therefore, by contradiction, our proposition P, and if you define P before, you can just write capital P, is true. And that's it for the first exercise. So let's move to the second one now. On the second exercise, we have x plus 49 over x greater than or equal to 14 for all positive real numbers. And we need to prove that this is actually the case by contradiction. So again, going through the 5-step process, we are going to write the proposition x plus 49 over x is greater than or equal to 14, and this is valid for all real numbers, for all positive real numbers. And we're going to assume not p, which in this case means that x plus 49 over x is less than 14. Now, what we can do here in order to manipulate this inequality is to write x as the common denominator on the left-hand side. So we have x squared plus 49 over x is less than 14. Given that we're talking about a positive real number, we can cross multiply the x without changing the direction of the inequality, which gives us x squared plus 49 less than 14x. Now moving every term to the left-hand side, we get x squared minus 14x plus 49 is less than 0. Now this is a perfect square trinomial, a expression with 3 terms which can be written as the square of a binomial. And which binomial are we talking about? This is x minus 7 squared. So in a nutshell, what we have here is x minus 7 squared is less than 0, which is a contradiction. And why is it a contradiction? It doesn't matter what number you plug into x. When you subtract 7 from it and you square it, you get at least 0. And it's important to state the reason why this is a contradiction, which is a contradiction given that the square of any real number and let me not be lazy here and actually write real, so of any real number, is at least 0. Therefore, by contradiction, P is true. And there you go. This is exercise number 2. Let's move to exercise number 3 now. Now, lastly, the exercise that involves inequalities and trig. Prove by contradiction that for all numbers between 0 and pi over 2, these are the values that theta can take. Sine theta plus cosine theta is less than or equal to root of 2. Now, we're talking about the first quadrant, so sine theta and cosine theta, they are both greater than or equal to 0 in that interval. So let's write that to keep this in mind. So let P be the following proposition. Sine theta plus cosine theta is less than or equal to root of 2 on the first quadrant. Now, as you know, we're going to assume not P, which in this case means that sine theta plus cosine of theta is greater than root of 2 for some theta which is in this interval. Now let's see if that's actually possible to have that value for theta in which the sine of theta plus cosine of theta is greater than root of 2. Now what we can do here is to first remove the root. We are going to square both sides, and given that sine of theta and cosine of theta, they're positive, squaring both sides will not flip or change the direction of the inequality. So we have sine squared of theta plus 2 sine theta cos theta plus cosine squared of theta greater than 2. Now, knowing that sine squared of theta plus cos squared of theta is equal to 1, we can rewrite this inequality as such, and we can subtract 1 from both sides. Also, another trig identity that we're going to need to use is 2 sine theta cos theta can be rewritten as sine of 2 theta. Therefore, so what we get is sine of 2 theta is greater than 1, which is a contradiction. It doesn't matter which arc you have, sine of that arc will always be in between -1 and 1, including obviously -1 and 1. These are also possibilities, but always in this interval. So this is a contradiction given that sine of 2 theta has to be in between -1 and 1. And in the previous statement, we got sine of 2 theta, which is greater than 1, so it doesn't match. Therefore, by contradiction, we can state that P is true. And there you go. This was the last example out of 3 on proofs by contradiction which involve inequalities. I'll see you on the next one.